name is Ilya Martynov. I work at LW'14, and I'd like to give you a presentation on Lua as a business logic language in high-level applications. And I'd like to talk about our design choices in those high-level applications, some challenges we met, and the ways how we try to solve them. Okay, so first of all, I'd like to tell some relevant company background. So we work in health industry. This means internet advertising systems. All those annoying banners you see, we kind of somebody to blame for this. And one interesting company structure is that we don't sell complete products, but instead we specialize in custom development, what means that we don't really have a single code base which we offer a single product, but instead we have to do customization work for our clients to suit their special needs. And this affects technology in certain ways because all your technology stack needs to be extendable and it should be possible to maintain multiple different parallel projects in this scene. So one of the components of the stack which I will be especially talking about is our custom web server, as it is where we use Lua extensively. And the core of the server itself is written in C++, but it uses Lua as an embedded scripting language for business logic. Before I speak more about design, first of all, I'd like to talk about certain requirements. First of all, it's defined with what you can call high load, and there is a relatively complex logic inside of the server about what adds show on each impression, and likewise there is some complex logic how to check events on those ads, how to calculate money relevant to ad server and so on. And another aspect which is special for ad server domain is that per transaction costs are quite important because how much money you earn per single request, it's not very high value, and the common statement that hardware is cheaper than developer's time is not quite true, or at least the balance is not the same as it's often for many other web projects. And to give you some feel what means high load, this graph taken from one of our bigger projects, and this says that at peak time we have almost 500,000 requests per second. And another graph I'd like to show is that this shows average CPU time we spend in each request, and you can see that the scale we're working is several milliseconds per request. Okay, so how did we come to use Lua? So the very first version of server was written in pure C++. We brought it this way, and we didn't do any existing software, mainly because we were very concerned about performance, and we had a feeling that we can make a better job. And the project succeeded, it ran very, very fast, but the problem we met is that development in pure C++ is quite slow, especially in our context, given that we have to do custom development, we don't really have, in pure C++ model, we couldn't have a single server, we need to have separate codebase for different projects, and it didn't really work out. And another problem is that while developers who can write low-level code and can solve interesting problems like finding memory leaks or chasing lost pointers, the problem with them is that they can't really write business logic code, or at least it's very hard to find people who can do both. My personal fear is that people who write in pure C++ all their life, it causes permanent brain damage to them, and they just cannot write code which is not about, say, creating log-free containers or something like this. And so we thought that the initial balance between performance and how we can develop it's probably wrong. We can shift it a bit, and we probably can find a better balance between speed of development and speed of running code. So what do we do? We took the idea of what I call separation of church and state, which means that all the core logic, low-level logic or performance-critical logic should be written in C++, should be shared code, but for high-level business logic, we should be using scripting language. And since it's so high-load, we need to find something very fast. So what do we choose? Well, obviously, since I'm standing in the conference, not in Python conference, we use Lua. And more especially, these days we are using LW'14. Initially we started with Stockholm, but later switched to LW'14 for better performance. So why not? I'd like to say that it's because I wanted to make this presentation, but it's not quite true. The real reason we use Lua is this one. World of Warcraft use Lua, or many other games use Lua. So the game community, the game developers, they have very similar use case as ours. On one hand, they need to write very fast code, but on the other hand, they'd like to make the development faster. And one of the ways they do it, they expose the gaming logic, or what in our world called business logic, in scripting languages, in particular Lua is very popular choice. And why game developers like Lua? It's probably the fastest scripting language. It's one of the easiest to embed, and it's very simple. What means that it's easy to train new people to write Lua. And another useful property, which is not probably not as important to us, but very important, is that it can be sandboxed. The sandboxing is not hidden, but I think it's the best one you can find in scripting languages. So it's fair to ask why one might not want to use Lua. And I'd say that as a general purpose programming language, Lua is not the best choice, mainly because of poor library support. One example which comes to my mind is that when last time when I was looking for XML library, they really sucked, at least if you compare it to what you can find in Perl or Python. But if you use this embedded language in a very special domain, and at 7, I think you can say it's a very special domain, it's not as big a deal because you won't find existing libraries for the type of business logic you implement anyway in any language. So now I'd like to talk about architecture. As I said, the ad server is C++, it's multi-threaded server. We have relatively simple design where we have dedicated worker threads. Each one thread per CPU core, and this is where the main logic runs in. There are some additional threads which do logging and so on, but all the interesting work happens in those worker threads. And each worker thread has one Lua interpreter state. In each the state we run multiple coroutines. And the general idea is that each new incoming HTTP requests eventually creates a new coroutine in the next idle loop interpreter state we can find. And the code runs in sandbox environment. Only some subset of flow standard library available. For example, no file, no EO libraries available, only some subset of debug or OS libraries available. And instead, we give some high-level input-output APIs to access external world, but it's restricted strictly to those cases which make sense in our domain. And general idea is that we allow only what is really required. It's the general idea is that we don't really want to give our business scripting team a huge list of policies. Instead, we just make sure that they can't really do things which don't make sense. Why do we have multiple coroutines in low state? So because we do expose some input-out EO API, particularly networking, it means that individual, when you when you process specific request, low code which handles this request may have to wait for responses. It's for a request it sends to external world, and you don't really want your Lua interpreter be idle while it waits for all these responses, because we have only that many Lua interpreters as you have CPU cores. So what we do is that our networking APIs, or generally any APIs which from the viewpoint of Lua code can be blocked, what happens is that internally they result in coroutines be paused until response is available, and meanwhile the worker thread can do processing of other requests. One of the core goals of API design is to hide as much complexity from Lua developers. Instead, we push it into C++ level. And I'd like to give you one example how we design our networking APIs. So what we don't want our developers to be concerned about a sync model or about multi-threaded models. From their viewpoint, handling of specific Lua requests should be a purely sequential code. And how we do this? On all such APIs, we always separate operations which create requests and from those which wait for requests. It's kind of similar idea what is called future or promises, which came from concurrent programming languages. The idea is that when you create future object, it launches parallel execution, and the main calling code doesn't get blocked until it asks for result. So if you create multiple futures and only then ask for results, you effectively can create multiple parallel requests. And in code it looks like this. How our HTTP client API looks like. You have a function called HTTP requests. It's on the upper side of the slide, which doesn't return you a response, but instead returns you an object, which you can put in some variable or table, and later you can ask this object to return you the result of this request. And the separation called get, it's a bit confusing. It doesn't mean that HTTP request is get type. It's just returns the response. So this simple, relatively simple code structure allows you to create multiple HTTP requests which all run in parallel. Okay, so since I mentioned word business logic multiple times, I'd like to elaborate what it means in context of AD7. So to simplify a little, the two main things you do in AdServer. The first one is you have logic which selects ad creative for banner which you show, and another activity which you do is you track various important events on ad creatives you have shown, like clicks, conversions, and so on. And from technical perspective, both these activities correspond to certain incoming HTTP requests. And tracking events is a relatively simple thing. You mostly just do login on them. And the most interesting part is selecting ad creative. So I'll talk a bit more about this. So selecting ad creative, it means you normally have some pool of ad campaigns you run, and for all those ad campaigns, when you want to select a creative, first of all you filter out ad campaigns which don't pass targeting. Targeting means that, for example, your ad campaign may say that it can be only shown to users in Brazil. And if you show it to user in Moscow, it shouldn't be shown. And there are some campaign delivery optimization rules, like you shouldn't show this ad campaign because for this user it has low click probability. And there are some, finally, when you end up with some list of candidates which you can show, you want to choose one which earns you the most money. And finally, there's some accounting, like how much advertiser pays to you, how much you should pay to publisher, and so on. And in the real code, it's not quite real code. I simplified it a lot, but generally it looks something like this. And what I really wanted to show on this slide is that the logic which happens here, it's all just iteration over usual low data structures. There is no calls to external database or something like this. All the information about ad campaigns, it's all represented to low code as low tables, hierarchy of low tables. And this was one of the basic designs we had, is that we represent all the business data as low data. It works for our domain because for us, most of the data, not all, but most of it can be considered as read-only, because you don't really create that many new campaigns every second. You don't change them that often. It's relatively slow changing configuration. And also the amount of this data is relatively small. There are maybe several thousands of ad campaigns in big project. It's quite realistic to keep it in memory. So what we did is that we just used low data structures as in memory storage. The advantage of this approach is that it leads to very natural low code, because it's all just iteration of low data structures using all the low constructs you are very familiar with, like pairs, and just some comparison that this field in table has certain values, so on. And also it's very fast because it's in-memory data, native in-memory data. It's pretty hard to beat. But eventually we found a problem with this design, which is given on this slide. It's being out of memory. Why did it happen? So there are several problems. First of all, you can't share low data between low interpreted states, unfortunately. And it means that, given our basic design, that we have as many low interpreted states as you have CPU cores, you have to keep multiple copies of the data. And when we just started with this business, I think the typical server had 4 cores. In these days, we use 8 core boxes, and I guess in the future the number will only increase. And also what happened that projects also became bigger. They started to have, well, more data, more campaigns, and so on. Another factor which doesn't quite help is that we use LW'14. And what I want to show you that there are some limitations on memory, particularly if you have 30-bit Linux and you have 32-bit application, you have only 3 GB of memory available to it. It's not a limitation of LW or LW'14, it's just a limitation on any application. And likewise, if you run 32-bit application on 64-bit Linux, you have a bit more. But if you upgrade, if you run 40-bit application, 40-bit Linux, well, all the RAM usually available to your application, but unfortunately, LW'14 can only use 1 GB. And the reason for this is that, for various interesting technical reasons, internal LW'14 still uses 32-bit pointers, and it requires that all the data it allocates for its own purposes should be able to address it by using 32-bit pointers. And on Linux, at least on Linux, it allows you, at least without some special hacks, it allows you to get data from low memory regions only up to 1 GB. So, annoyingly enough, if you upgrade to 40-bit architecture, you get less memory. And what also doesn't help is that it's all the memory for whole application, for whole process, and you have multiple threads. It's all separated, in our case, by 8. In case of 8 core boxes, which means that you don't really have that much memory, really. What solutions we considered? One solution is maybe switch to stock LW'. This assumes that we switch to 64-bit architecture, which obviously doesn't have this special limitation of LW'14. But we're kind of reluctant to do this because it gives us performance penalty, and in our case, it translates in real money. And also, we have a feeling that it's in certain way a dead-end approach, because both LW and LW'14, they have a problem in their garbage collection system, which is not really designed for a very big amount of objects. What you can find that if you have many business objects, if you have too many objects, garbage collector cannot delete, cannot process the data quickly enough. It starts doing garbage collection pauses, which take significant amount of time. Okay, so the next idea we had is to move business data out of LW, which means that instead of allocating all these data structures for business data as LW data, we create some storage managed by C++ code and somehow expose it to LW logic. And the problem is that we need to make this scheme somehow backward compatible with existing code, which expects to have just ordinary LW data. So how could we do it? The first approach, which doesn't rely on any special functionality from LW'14, is just to use user data. User data, if you don't know, it's a special LW type in LW, which allows you to present well, any kind of data managed by your own code in LW. And if you add some metatables to it, you can, in certain, you can sort of fake LW tables. You can represent the data structures managed by by your C++ application as low data. But the problem is that every time you access a field with user data, if we use user data as a fake tables, it means it's a C function call, and it's actually much slower compared to access to native flow data. And what we found with this approach, that our applications run significantly slower, like several times slower. The next try is to try use features which are special to Logit. I'd like to say that until this point, while we used Logit, we kind of use it as accelerator. We didn't really use any special functionality it offers. Particularly, all our code was fully backward compatible with stock Lua. At this point, we thought, okay, maybe we should actually use APIs which are special to Logit. So what is FFI? It's an alternative interface to C code from Lua, and it's supposedly designed to be Logit friendly, which means that it supposedly should be faster. And they have also, FFI has its own Lua type, which is called CData, which for the sake of this presentation can be considered similar to user data. It's not exactly the same thing, but you can use it in the same way. You can also put metatables to it, and this way fake Lua tables. Before I tell more about this approach, I'd like to explain a bit how Logit works. So what it can do is that it can run part of the code as interpreted mode or in JIT compiled mode. Interpreted mode is similar to stock Lua, except that a bit faster. So even if your code is not JIT compiled, it still usually gets better performance. And the reason why Logit may run parts of your code as interpreted and part of as JIT compiled is because it cannot handle certain code paths, certain code constructs or patterns. And in those cases, when it can, it falls back to interpreter mode. But usually, as long as your hotspots are covered, you are good. But with the problem you can meet, especially if you have existing Lua application which was never written with Logit, especially with Logit in mind, like it was in our case, you'll find that practically none of your code JIT compiles, simply because you really have to target Logit when you write code, otherwise it doesn't compile it. And until we introduce FFI, it's not a problem because it still runs faster than stock Lua. But with FFI, when you introduce FFI, you have to make a certain leap of faith, which I explain with next slide. Here I want to present you benchmark results. It's not a benchmark we did. It's a third-party benchmark, but it's very indicative. It's very simple micro benchmark. It iterates over some data structures and runs over them simple algorithm. The details are not quite important. What important are the numbers. So you have here 3 columns. One, the same code written using FFI and CData, and other 2 columns use native flow data. There are 2 variants, but the difference between are not important for this presentation. And the same code was run in Logit with JIT compilation turn it on, and turn it off, so we force code not to compile. And what you can see that when you do have JIT compilation on, FFI beats native flow, but if it's not, you have huge penalty, like it's 10 times slower. So what it means that if you have your legacy application which use all this data, and then you suddenly change this data to use FFI, because your code doesn't compile initially, it actually starts to run slower. until you manage to fix your application to have JIT compilation on most of parts of it, you get huge penalty when you introduce FFI. So how can you make JIT happy? How can you reach this goal of better performance? There are some tools there. Unfortunately, they are not quite user-friendly. You can, particularly, you can get compilation traces which tell you why a certain code doesn't compile. But the problem is they're quite hard to interpret. I show a simple example on this slide. If you don't spend much time debugging logit compilation traces, it all looks like gibberish. It basically says which part of code, but then there is a message at the end with some message which doesn't really tell you much. In a loop and root trace, what is it? I have no idea. Yeah, they have a wiki which lists common code constructs which don't compile, but it's very brief and not quite complete. There is a unique challenge with logit and FFI is that unfortunately it requires very special low-level knowledge to make your code run fast, and even once you understand what's the problem, you probably can rewrite your code in a way which is low-friendly, but one of the problems is that it doesn't necessarily means to better code from the point of readability, or it might lead, or at least some transformation are not quite obvious when you start. And I want to give you a very simple example. So you can see here 2 lines. The difference is just 2 brackets. And I'd like to ask audience for any guesses which line works better in JIT and why. Any ideas? The second one is better. Any ideas why?
Multiple returns.
Yeah, good idea. So it's not actually multiple returns, but the thing is that second line, the first line is interpreted as tail call, and tail calls to built-ins for some reasons cannot be compiled in current version of logit. But no, the second is not tail call. Yeah, tail calls to built-ins.
For 2.0, right?
Maybe. But it's a moving target.
Yeah.
We don't use 2.1 because it turned out to be unstable in our cases.
Okay.
So here it is. There is a change with logit is that it breaks out abstractions. Our idea was that we hide complexity flow from low developers. All the complexity should be on the side of C++ developers who write the core logic and low-level bits. But unfortunately, it seems that abstractions leaks in this case, and we have to solve this problem somehow. And it's project in progress, so we don't really know the good solution to this yet, but we're trying.
There are no good solutions to this, I'm afraid, at this point.
Okay, so I'd like to wrap up on this at this point, and what I want to say is that while low technology in general, I mean not just stock low JIT, overall it maybe offers unique challenges, but it also offers you opportunities to do very complex things and fast, and despite everything, it's very powerful, successful technology, and I'd like to give a credit to Lu community for this and thank for all your work. And I guess that's it. So, any questions?
I have the question, why do you need so much memory?
Um, well, because we have a lot of data, but we still try to fit it all in memory.
But the advertising in this much memory, do you hold the actual payload there?
No, we don't keep actual creatives. If you, like, we don't keep actual images of Flash, but you have a lot of information about ad campaigns, like all the strict rules, where you can show them and so on. It's quite a lot.
What format are they in?
We load them in form of JSON file, but it's like the implementation detail.
Have you tried to compile them to lower code?
We load them as JSON file, but we compile them to low code.
So you have more than 1 gigabyte or 1/8 of gigabyte of lower code in memory, right?
Well, more, because we still run in production. We still run 30-bit applications.
Okay.
Because we have more memory there.
Okay. So Roberto,
have you considered using weak tables plus meta tables for your data?
Not really. What we found is that any games with meta tables, they're usually slow.
No, because with weak tables, I mean, you have a kind of cache. You use the meta table to access, but then you put in the table and keep it there until at least the next GC cycle.
So some sort of caching.
Yes. It's very easy because you just make the table weak.
I think we did try to have some sort of caching, but it's complicated and it doesn't work as fast anyway.
It probably kills lower JIT performance anyway.
Yeah.
So lower JIT profiling and optimization, is it still magic for you, or is it engineering?
Yeah.
Magic.
Yeah, it's magic. Defined magic.
Okay.
When you said about your out-of-memory problem, my first thought was making a web server UDP and hold all the data in one instance, and all other instances would access this server over localhost UDP. So the timeout, the latency would depend on lower socket library and the Linux kernel alone. So I wonder, have you considered it? Have you measured it? How much it would be slower than your final solution?
So you mean put all the data in one process and access it from others?
Yes.
Well, it kind of the killer for performance, because we would have to make a very high amount of requests to this sort of storage. It's kind of like using database. One of the reasons why it all runs fast, because it's all local access in local code. If you try to use some sort of database, it will run like 10 times or 100 times slow, and it also kills opportunity for doing complex logic of it.
Okay.
Hi. What about atomic operations in your framework? How do you perform increment, decrement? It's very important for the billing.
Sorry?
It's very important for the billing.
Could you repeat?
The atomic operations.
Yeah. Okay. Not really important. I mean, there are some parts where you care about atomic operations, like when you track impression counts. But again, not really. If you're tracking, for example, things like number of impressions, it usually gets handled on a low level. On the next level, when you do things like you do impression, you log it to files, and then it gets processed it's get handled by a offline process. You don't really need to check that many things in real time.
You can survive a few extra impressions outside of the budget, right?
Yeah, definitely.
So you don't need to be atomic.
You don't really need to be very exact, simply because in our world there is thing about discrepancies, like when you think you show 1 million impressions, your client says that you showed 5% less, and it's simply because they use different tracking methods. In these cases, doing very high precision count simply doesn't make sense. It doesn't really matter.
Do you save your data on disk? You use in memory a solution, and what about saving the data on disk?
So the data we have, it's actually can be separated into parts. There is configuration data, information about campaigns, which is kind of static, and it comes from outside. It comes from configuration UI. But then there is data about for example, about users, how many impressions and what we've shown them, and this actually gets stored in key-value database.
Did you consider to use Redis and so on?
We use MongoDB for user data.
Okay.
So I guess it answers this question.
How do you reload all those gigabytes of targeting rules?
We start a new low interpreted state and then kill the old one as soon as finish all requests.
Okay. Next question.
At the beginning of your presentation, you said that you wanted your developers to concentrate on high-level business logic. And you finished your presentation that in order to resolve memory issues, your developers should have low-level knowledge about low-JIT. Isn't it a bit contradictory?
Yeah, it is. And this is why I said it's a challenge for us. We need to find a way how to manage this complexity, and it's a project in process. We don't really have a good answer to this. We probably will make some tools, better tools than Logit has itself to find bad patterns and so on. Maybe make some coding policies and so on.
They say.
I think you you have to find those rare animals anyway, about which you spoke.
It's pretty hard. Just to give you some context, our C++ team is several people, and our business team who writes in Lua, it's several tens of people.
Several people and several tens of people?
Several tens.
Oh, no, not that many people in Moscow.
Yeah,
doing that kind of programming?
I think we are probably the biggest Lua company, at least in Russia, I suspect.
I got that. They say that LoaJIT is the new Lotus Notes, I believe. One change and it's all bad.
Well, we'll see.
Okay, thank you.